Thank you for watching Knowledge Academy.
Before we start Stokes' theorem, we're going to be talking about physical implication about Stokes' theorem, and it's a little bit complicated, but we need to use some sort of analogies to understand the Stokes theorem. So let's write the definition, and then we talk about some analogies to understand this theorem. So Stokes' theorem states that the surface integral of the curve of a function over the surface bounded by a closed surface is equal to the integral of the particular vector function around that surface. So what exactly it's saying? Think about it. First thing is that what is the surface? The Stokes theorem says. It says, if you remember earlier, we talked about divergence theorem, and divergence theorem is that you know, divergence theorem says that let's suppose we have the divergence theorem is calculated. If you have a little heater inside this room, right, and this heater you provide the electricity, and this heater actually producing the heat, and heat is going into the room. All this heat is going to be passed from these walls, and once this heat passes from the wall, whatever comes out from the wall, divergence theorem is going to be calculating all of that. What is the Stokes theorem? Stokes theorem is a little bit same kind of term, but in a little bit different domain. And this Stokes theorem says that if this room have a little window, right, and I want to know how much heat going into the system and coming out of these walls, I can say that, well, where the heat going into the system? So is this red color boundaries, and there should be an angle of these travel. Here we have no angle or direction. We don't have any clockwise or anti-clockwise things. But Green theorem talk about the orientation of the curve, positive orientation of the curve. So if you're seeing from this side, right? So this is your eye. If you're seeing from this side, whatever is going into this window, from this window, whatever is going into the room, that's gonna come out. So if I'm gonna say this red thing is going into the window, whatever is there, maybe air, maybe hot air, maybe light, maybe magnetic field, this red should be equals to the white field, right? This white field and red field should be equal, and that's exactly what the Stokes theorem says. Another way another way is that we need to add another complexity here, and the complexity is we should be defining a line, right? So if I'm going to take a line, if I'm going to be defining a line like this line, see, I'm defining this line. So if you consider this green line is normal to this window, then I want to know that all the things are coming out, how much in the direction of this green line. So that should be normal. And this one is should be here is also normal. So they're coming out and then coming in. Right. Another way I'm gonna look into this one. In this image, if you can see here, whatever is coming out, or this test, let's suppose this is a window. This is a window, right? And this is the arrow, it means you are going this direction. And whatever is going into this window from this direction, I'm going to say whatever is going here, it should be equal to whatever comes out, right? But I have to make sure that everything should be normal. Everything should be normal in certain direction. So if I'm saying something going into the system like this way from this room, from this window, whatever comes out, it should be in the same direction. That should be equal to each other. That's exactly what the Stokes theorem says. Another ways you can see here, we need to understand this theorem by analogies. Otherwise, we cannot understand. Let's suppose it's kind of like a half. You take a hard potato and you cut it into pieces. The heat going into the system, which is bottom, like this red color curve, right, and it's going into the system. And what I can do, I can use the line integral to calculate this line to whatever field going into the system. Then I'm going to use this green theorem, green lines, to finding the flux or field coming out of the system, but should be circulation. So what I use the circulation. This is a circulation, right? And I can make a small dots around these. Maybe I can make here and then coming out towards you. It may making here coming out towards this way, called n, all n, right? So the things going into this hard potato from this half portion in the bottom should be equal to the things coming out of these little patches, which we call differential patches. I can write this. I can write this whole phenomena like this. That is my line integral around the curve f dot dr. Remember, this my line integral is equal to the curve of this surface, this whole surface, with the field. We know this is gradient and this is the field. And we taking the integrate over everything. So this is one is ds, this one is ds, this whole surface is s surface, and this is s. The whole surface of blue surface is s. Same thing, blue, this whole surface is s, and this curve is c. So I'm gonna write here ds. And that is, I'm gonna write here where c a closed curve, s any surface bounded by c. And then f a vector field which is using or affecting this curve C, right? Or we are interested to evaluate that. All right. Now we can also write this whole. We can also write D as different book using different kind of analogies and different kind of symbols. So I'm gonna say as this one is also equals to curl. Remember the earlier we used this dot f for the divergence theorem, and this is divergence DIVF. Same thing here is equals to curl. We learn about this curl. So curl f ds. Okay, we can also write this. So let's take a look problems to understand this phenomena a little bit better. Let's go here. Another example here. Use Stokes theorem. Evaluate where f is a vector xzi plus yzj plus xy, okay, such that S is a part of the sphere that lies inside this langle and above xy plane. Okay, so we have part of the sphere. So we have a sphere like this, and then we have a cylinder like this. So really what we have, we're going to be making a cylindrical shape like this, sorry, spherical shape like this. And then we have a cylinder inside. And this is my, my centers. And I have a cylinder inside. Okay, the equation of this curve is giving x squared plus y squared plus c squared equals to 4. The equation of the cylinder or the circle is given x squared plus y squared equals to 1. So now what I'm going to do, I'm interested to know more into this area. Right? That is my C is going this way, and that is my S, my surface that I'm interested. This guy is 0, starting from 0. Okay, so equation of the sphere we already wrote, equation of the cylinder. So we're gonna write equation number 1. And cylinder or sphere you can call it, sorry, circle you can call it. Subtracting 2 from 1. So if I do subtracting 2 from 1, it's going to be z squared equals to 3 and z equals to plus minus 3. So I'm only interested in plus. Since z is positive. Right, so this circle is going from 1 to 3, and then the vector from C is given by the RT just like we used to do our line integral. So basically Stokes theorem is an integration of line theorem and surface theorem. They just are a combination of the two. And RT is going to be cosine t plus sine t plus square root of 3k. Right? There's no t here, and I'm going to be just this is x, y, z pretty much, and I'm just substituting the value, and I'm gonna the unit of this circle is 1, so that is why I have 1 1 here. Right? What I'm going to do, I'm going to say is t is going to go from 0 to 2 pi, because t is going to make complete circle, and I'm going to be just taking the integral of this, a dot product for f r t, and is going to be equals to, let me just do this, rt prime is equals to minus sine t plus cos t, and then j, and then this is the height. I just take the integral of this r. So what I'm going to do, I'm going to multiply the two, so it's going to be in my, if I substitute into my equation, like this equation, the function, so it's going to be 3 square root cos I plus square root 3 sine j plus cos t sine tk. Okay, and now I'm going to be writing my integral, so I'm going to write in this square f ds. Left side is the one I write, right side is the one I solve. Right, and it's going to be d. I can also write this right side, I can also write like this. And f r and then r prime t dt. Write like this, 0 to 2 pi minus 3 cosine t sine t plus 3 sine t cosine t dt. And then I can take the integral, so I'm going to say is here 3, and if I take the integral and substitute the, take the integral for this one, this is basically going to be cancelling out with nothing left over 0 dt. And if I take the integral, I don't need to take the integral, nothing left really for any term with t, and it's going to be 3 times 0, so answer is 0. So really nothing going into this system, and could be the reason is that because really this curve is here, nothing can be, this curve is closed, so nothing can be just, basically there's no room to some quantity going to the system, right? Look other problems. Use Stokes theorem. To evaluate this function is given ds, where some of the books actually calculating this kernel with taking that cross product of these. So they solve like literally like this. I'm going to be doing the problem, and then after you getting a function, you can solve this one too. You just need to have a little bit different approach. We right now using line integral to solving this problem, but you can do actual. You can take the cross product between the f and gradient. Okay, y x cube k. and S is a portion of the sphere of radius 4 with z bigger than equal to 0 and upward orientation. Okay, let me just draw a quick diagram for this one. It's going to be pretty much the same kind of shape the one we discussed earlier. It's like a hemisphere. Okay, if you see from the top, right, it's going to look like a circle, and let's look like this, and it goes up to r equals to 4 is given here. Okay, now here in this case I need this s. This is my curve and that is my s. That is my curve is going to go this way, and the upward orientation is this one. This is the upward orientation for this. So what I'm going to do, I'm going to be writing we are going to use Stokes theorem the following direction, and direction is alright. In this problem we need to find out, we parameterize our curve because line integral always we do. So I'm going to write the r r cos theta x y z, simple is x y z for the bottom of that. So x y z, x equals to r cos theta, so r cos t, r sin t, and then z equals to 0, and the parameters t is going from 0 to 2 pi. I'm going to write here the z component of the parameterization is 0 because the c lies on the xy plane. Right. So z value is 0. Now I'm going to take my function or my field and substitute these parameters, and then I'm going to take the dot product. So I basically doing this part before I substitute in the integral, and I'm going to take my, so 4 sine t minus 4 cos t and xy cube, right, xy cube here. So y, y x cube, sorry, y x cube. So if I multiply 4 times 4 times 4 times 4, it's going to be 256 sine t cosine cube t. And my second part, which is r, I'm going to write as is all I did, I just take the, this is the, remember, this is the prime, like this, take the prime of this. Let's try to take the dot product. We'll take the dot product. It's going to be minus 16 sine square t minus 16 cos square t, and nothing left because this guy is going to multiply, this is going to be 0. So this is pretty much what we have here, and I can substitute 16 minus sine, so sine square t plus cos square t, and this whole thing will be 1, so it's going to be minus 16. And I'm going to substitute into my integral. My integral equals to, and I'm going to write in the left side is the one I just wrote, the right side is the one I solved. Okay, and here I'm going to be substituting 0 to 2 pi. This whole thing I just did 16 with minus sign and then d. If I do this, is going to be 16 times 2 pi minus 0, so it's going to be minus 32 pi. Okay, okay, now let's do a problem where I'm going to do a little bit different approach to solving this problem. Let's see be the orientation of a triangle. Orientation, I would say orientation, so oriented triangle. Laying in the plane 2x plus 2y plus c equals to 6 as shown in the figure. I'm going to draw the figure. Evaluate this. Okay, and the figure will look like this. And this triangle is going to be going to 6 here. This is my surface. It goes 3 here, goes up to 3 here. Right? So 2, 1, 1, 2, and this is 6. So I have 3 curves. If I'm going to say here, I have 3 curves, C1, C2, C3, and upward normal, right? And basically it's coming up towards us. And this is a normal we need to calculate. Everything goes into this. The surface equation is given, right? First thing first, this guy is giving x plus y equals to 3 is given in the problem. So that's a line equation. S is given, the surface is given, 2x plus 2y plus c equals to 6. I forgot to tell the field f equals to, so f x y z field equals to minus y square I plus j zj plus xk. So what I'm going to do this time, I'm going to find the curve, right? I'm going to find the curve and then substitute directly. So I'm going to be, I usually use this curve f ds, right? So what I'm going to do, this time I'm going to be finding the curve to solve this, so I don't have to use not too much line integral approach. And curve should be taken by a cross product of, this is basically a cross product of gradient times f, and this gradient is I, j, k. Gradient is nothing but partial derivative of x, y, z. I told you that you always writing gradient first, so you should be have this gradient line here. If you reverse it, writing gradient later, all the signs flip, and your answer could not be a correct answer because cross product is direction oriented. So let's do this. This one is going to be minus I minus j, and the last one will be cancelling this. It's going to be, this one is 0 minus and it's going to be plus from the formula, and then I'm going to take this one, so 0 minus then minus 2y. So I can write this minus I minus j plus 2y k. Considering our surface to z equals to 6 minus 2x minus 2y, that is my z. All I did, I just take everything on the other side, so it's look like this. And now I'm going to be writing my Stokes theorem. Curl f dot nds. You can write dr or ds with the target, the vector symbol, or you can write n. N is basically a normal vector. Okay, and now I'm going to be substituting everything. So let's go to the next slide and substitute. So I'm going to write in the right side the one I calculated with the curve of the function. Is a partial derivative of I minus gy partial derivative of j plus k and then dA. This is my, basically this side I said. All I did, I just taking the, I write this a unit vector, right? And I'm going to see if I can substitute the value now. Minus I minus j plus 2yk. And now this one is my 2i 2j. I'm going to take the unit vector for 2i 2j plus k. And let's substitute the limits. So I'm going to write dx dy, and here if I take, it's going to be this to this, going to be minus, so this one is 0 and it's going to be 2y minus 4, right? 2y minus 4. and the limit for x is gonna go from 0 to 3 minus y. You guys remember here in this, where is that? Yeah. This equation, I'm going to write is equals to 6 minus 2x minus 2y. So z becomes 0 and I need to find the value of x. So it's going to be 3 minus y, and if I substitute the y equals to 0, then I get the second value 0 equals to 3. Right. Now I'm going to take the integral 0 to 3 minus 2y squared plus 10y minus 12 dy. I apply directly integral and limit, and then if I'm going to apply second integral, it's going to be minus 2y cube over 3 plus 5, 10 divided by 2 is going to be 5y squared minus 12y 3 0. If I substitute these values, these 3, so it's going to be minus 2 3 cube over 3 plus 5 3 squared minus 12 3, and then minus 0. This one is going to be 2 to 9 times minus 9, and then times 2 is 18 plus it's going to 9 times by 45 minus 24 36. So let's do 36. 18 so my answer should be minus 9. Okay, let me do another problem. A liquid is swirling around in a cylindrical container of radius 2, so that its motion is described by the velocity v. So they're going to be c2 and minus y okay, as shown. Find this. Okay, this S is a surface cylinder. So what I'm going to do, I'm going to be just simply go and then make it simple. If I do this curve technique, and I'm going to find I, J, K, all my gradient vector, and then substitute the component. And if I take this one, the answer would be 3. Right, this is going to become, so I'm going to be writing my curve f and ds equals to, I'm going to write like this, 3 du. Okay. Now what I'm going to do, I'm going to convert this whole thing into cylindrical curve. It's a cylindrical, so I'm going to go to cylindrical curve. dA equals to r dr d theta, and r equals to r square equals to x square plus y square. Okay. So what I'm going to do, I'm going to write in this lower integral and writing this 3 r, this one is equals to r, and then I have another r, let me just do other way, parenthesis should be contain this, and then r dr d theta. Dr is first, yeah, dr is first, so it's going to go to 0 to 2, and then theta 0 to 0 to 5, right? Radius is given here 2. Now it's fairly simple. If I'm going to take the integral, so it's going to be 0 to 2 pi, and then r cube divided by 3 is going to be, when you take the integral, is going to be divided by 3, 3 cancels, is going to be 1, r cube, and it's going to be 2 to 0, and then d theta. I substitute the value before I take the second integral, and it's going to be 8, 2 times 2 cube is 8 d theta. Let's take the integral, and the integral will be 8 2 pi minus 0 and 16 pi is my answer.
Thank you for watching Knowledge Academy. Please subscribe my channel.